If a meteor were to strike a major data center right now, the uh, incredibly brilliant multi-paragraph answer that you just posted on your favorite app might actually vanish forever.
Oh, yeah. Completely gone.
And the craziest part about that is that the data loss isn't a glitch. It is a deliberate, calculated engineering choice made specifically so your app loads just like 1 second faster.
It's all about the trade-offs, right?
Exactly. So today we are cracking open the architectural blueprints of one of the internet's largest Q&A platforms. We are doing a deep dive into a comprehensive system design study detailing the architecture of Quora.
Which is such a fascinating case study.
It really is. We are going to be decoding that massive invisible machine that's just, humming in the background every time you type a question or scroll through a personalized feed. We've got a whole stack of sources today. They cover the raw math of the user traffic, the initial system blueprints, the inevitable and catastrophic bottlenecks, and then the final architectural upgrades required to keep the whole thing from crashing down.
And it takes a lot of upgrades.
Oh, for sure. Okay, let's unpack this. Because before we even look at the servers and the code, we have to understand the sheer weight this system is trying to lift. Why is a platform like this fundamentally different than, say, a standard search engine?
Well, it really comes down to a fundamental shift in user intent. Like, if you think about a traditional search engine, the interaction is heavily skewed toward reading.
Right, you just want a quick answer.
Exactly. You want to know the capital of France, you query the database, you get Paris, and you bounce. It's a very fast, shallow, stateless transaction. But a community-driven Q&A model is it's conversational and incredibly deep.
Because you're dealing with real people.
Right. You are asking questions of other humans, which means the system has to support this highly interactive, bidirectional environment. I mean, users are constantly writing these massive blocks of text, editing them, upvoting, downvoting, collapsing threads, commenting. The ratio of writing to reading is completely inverted compared to a standard search engine.
Which is a whole different beast.
Yep. It is a completely different and, frankly, much harder engineering challenge.
And the scale of that challenge, looking at the math in these sources, is just staggering to me. We're talking about 300 million monthly active users posting thousands of daily questions across, 400,000 different topics?
Yeah, and when you run the raw resource estimation for that kind of traffic, I mean, the numbers get astronomical very quickly.
I can imagine.
The blueprints we are analyzing, they make these baseline assumptions just to even begin designing the architecture. So they assume 1 billion total registered users, out of which 300 million are daily active users.
Okay, 300 million daily.
Right. And in system design, you use that daily active user figure as a proxy to calculate your peak load.
Meaning like the worst case scenario.
Exactly. It's the absolute maximum number of requests per second the system will have to handle when, say, a major news event breaks and everyone just logs on at the exact same time.
And the sources calculate that peak load at roughly 64,000 requests per second.
Which is wild. And it means, assuming standard hardware capabilities, you're looking at a baseline requirement of roughly 4,700 servers just to keep the application from timing out during those peak surges.
Wait, 4,700 servers just humming away to handle the raw traffic? That is huge. But honestly, the storage requirements are what really broke my brain here.
Oh, the storage math is incredible.
It says this system needs to ingest 118.25 terabytes of new data every single day. You scale that out over a year, you are looking at over 42 petabytes of data.
That's a massive footprint.
Just to put that in perspective for you, the listener, if you have a top-tier smartphone with like 256 gigabytes of storage, 42 petabytes is like filling up roughly 168,000 of those phones to the absolute brim every single year.
It's almost hard to visualize.
And the bandwidth demands hit 226.3 gigabits per second of just incoming and outgoing traffic. But I have to push back on this data volume a little.
Sure, go ahead.
If we're talking about a platform that is primarily known as a text-based Q&A site, why on earth is it generating over 100 terabytes of new data a day? I mean, text is incredibly lightweight.
Yeah, it's a very common misconception to view these platforms as purely text. While the text payload itself, the question, a multi-paragraph answer, maybe a few comments, might only account for about, say, 100 kilobytes per interaction, the math radically shifts when you factor in rich media.
Oh, right. because people post pictures.
Exactly. The architectural assumptions project that 15% of all questions contain an image and 5% contain a video.
And video files are just massively heavy compared to a paragraph of text.
By orders of magnitude, I mean, a standard compressed image might be estimated at 250 kilobytes, but a short video is easily 5 megabytes or more.
So it adds up fast.
It does. Multiply that across 300 million active users constantly uploading content, and the media files just completely eclipse the text storage. Furthermore, you have the hidden payload.
The hidden payload.
Yeah, the constant, never-ending stream of metadata. Every single time you upvote a good answer or downvote a troll or follow a new topic or bookmark a page, that action generates a state change.
And the system has to remember all of that.
Precisely. That state change is data that must be routed, processed, and permanently stored in a database.
Wow. Okay, so knowing the sheer physics of this data crashing into the system daily, the text, the videos, the millions of micro interactions, how do engineers actually build the plumbing to survive it?
Let's walk through the initial design, like the first draft of the architecture.
Okay, let's look at the first draft.
Assuming we all know the basics of load balancers sitting at the front door to route traffic, right? Like the host at a restaurant seating guests. And then distributed caches like memcache acting as fast, short-term memory. I want to look at how they initially structured the core application.
So in that first iteration, they relied on a very strict traditional separation of concerns.
What does that mean in practice? Well, they had web servers dedicated solely to handling incoming HTTP requests. They just terminate the connection and parse the data. Completely separate from those were the application servers, which handled the actual business logic.
So they were doing the heavy lifting.
Right, the complex code that figures out what to do with your request. And when an action needed to happen in the background, these servers communicated with a manager and worker system using manual in-memory queues.
The sources outline the API design tying this all together, and it specifically relies on RESTful parameters. Which makes sense, right?
Yeah, standard practice.
Because if you are a client app and you want to post a question, you can't just throw raw text at the server. You use a structured POCP method. The API forces the client to package the data neatly with a user ID, the text of the question, a topic ID, and any media files.
Exactly. It creates a standardized, predictable payload.
So the back-end application servers know exactly how to unpack it and route it to databases like MySQL or HBase.
Yeah.
Or to blob storage if it's a heavy video file, right?
Right. But what's fascinating here is how this initial design handles the offline recommendation system.
Oh, this part blew my mind.
Yeah, because you might intuitively assume that when you open the app, the system's application servers frantically query the database, look at your profile, and try to algorithmically generate a personalized feed of questions for you right in that exact split second.
Which would be computationally exhausting at this scale.
It would be entirely impossible. The latency would be measured in seconds, if not minutes, and users would just abandon the app.
Nobody's going to wait a minute for a feed to load.
Exactly. So instead, the design utilizes a fleet of dedicated compute servers that run machine learning algorithms completely offline, entirely separate from the live user traffic.
So they're just running in the background.
Constantly. These algorithms are asynchronously analyzing your historical behavior, your upvotes, the topics you linger on, the authors you follow. They calculate and compile your customized feed in the background and push it into a fast cache.
So the feed isn't actually generated when you open the app at all.
No. It was generated hours ago and is just sitting there waiting for you to request it.
It's an illusion of instant computation. I love that. But as brilliant as that offline processing is, the initial architecture as a whole was fundamentally flawed, wasn't it?
It had major issues under load.
Right, because the strict separation web servers, application servers, and memory queues works great in a vacuum. But what happens when you introduce the reality of 300 million daily active users showing up?
The system bottlenecks violently.
Violently, yeah.
The first major point of failure in that initial design was the very thing that made it look so organized on paper. It was the strict physical separation between web servers and application servers.
Because it forces data to physically travel.
Yes, it creates severe network I/O latency. In computing, the absolute most expensive thing you can do, time-wise, is send data across a physical network cable.
Because it's literally bound by physics.
Exactly. Every time the web server needs the application server to process a piece of logic, it has to serialize the data, send it over the network, wait for the app server to process it, and then wait for the response to travel back. When you multiply those milliseconds of network transit by 64,000 requests per second, the entire system just bogs down.
So to level this up to their final design, they execute a series of massive upgrades. And the first upgrade directly targets that network latency, right? They introduce service hosts.
Yeah, service hosts were a game changer for them.
Basically, they realize that separating web and app servers is a luxury they just can't afford, so they smash them together into these powerful, homogeneous units. A service host handles the web serving and the application logic on the exact same physical machine, completely eliminating that network trip.
It's a classic example of prioritizing raw performance over theoretical architectural purity.
Just make it fast.
Right. But the web servers weren't the only bottleneck. The databases were choking under the volume of read and write requests. They were using traditional MySQL deployments, and as the tables grew, the system was spending massive amounts of compute power trying to execute cross-node joins.
What does that mean, practically?
It means the system had to constantly pull pieces of related data from completely different database servers over the network and stitch them together before showing you a page.
Which is slow. And that brings us to upgrade number 2, vertical sharding of MySQL. We usually hear about horizontal sharding in system design, where you just buy more servers and split the rows of your massive user table, like alphabetically across them.
Yeah.
But vertical sharding is a totally different mechanism.
It is. It requires a much deeper understanding of your data access patterns. Vertical sharding is about reorganizing the data structurally.
Okay, how so?
Instead of splitting rows, you group related columns and tables onto the same physical partition based on how the application actually queries them.
Oh, I see. It's like reorganizing a massive library. Instead of just building a new wing and moving half the books there alphabetically, you take the test prep books and the study guides and put them on the exact same shelf. Because you know a student asking for one will almost certainly ask for the other.
That is a perfect visualization.
It saves the librarian from walking across the whole building.
Exactly. If the engineers know that rendering a question page always requires querying the question table, the author profile table, and the upvote count table simultaneously, vertical sharding ensures those specific tables live on the exact same physical server.
So it's all right there.
Yes, it completely eliminates the need for expensive, slow cross-network joins within the database layer.
Okay, but I have to push back on the reality of implementing that. Doesn't putting all related tables on a single specific server create a massive, terrifying single point of failure?
How do you mean?
Well, think about a localized traffic spike. If a massive breaking news event happens and 2 million people suddenly search for the exact same viral topic, all of those read requests are going to hit that one vertically sharded server. Won't that machine just melt down?
That is the exact vulnerability of vertical sharding. And it's why database architecture cannot exist in isolation. You are entirely correct. If that MySQL server had to actually process every single one of those 2 million read requests, its CPU would pin at 100% and it would crash.
Boom, site down.
Right. This is why the architecture relies absolutely on its distributed caching layer, memcached, to act as a shock absorber.
So the cache takes the hit for the database.
Precisely. When that news event goes viral, only the very first handful of user requests actually make it all the way down to the vertically sharded MySQL database.
Because the cache is empty at first.
Right. The database computes the complex query, hands the data back, but simultaneously stores that rendered answer in memcached.
I get it.
So for the next 2 million users asking the exact same question, the architecture intercepts their request at the caching layer and serves the answer directly from RAM in microseconds. The vertically sharded database never even sees the traffic spike.
It's brilliant. Here's where it gets really interesting to me, though. Upgrade number 3 involves completely ripping out one of their databases. The sources note that they were using HBase, but it was suffering from terrible latency degradation.
The latency spikes were a big issue.
Yeah, it's P99 latency, meaning the slowest 1% of user requests was hovering around 20 milliseconds. So they replaced HBase entirely with something called MyRocks. And by doing that, they dropped that P99 latency from 20 milliseconds down to just 2 milliseconds, a 10x speed upgrade.
It's an unbelievable improvement.
How does just swapping the database engine achieve that kind of massive performance leap?
Well, it comes down to the underlying mechanics of how data is written to the physical storage disk. MyRocks is a storage engine for MySQL, but it replaces the traditional storage layer with RocksDB. And RocksDB uses something called a log-structured merge tree, or an LSM tree.
Which is optimized for writing data, right?
Highly optimized. In older systems, when you write data, the database has to randomly search the disk for the right place to put it, which is physically slow.
Because the disk head has to physically move around.
Exactly. An LSM tree in RocksDB just appends new data sequentially to a log in fast memory. It just slaps it on the end.
Nice and easy.
And when that memory fills up, it flushes it to disk in one big contiguous chunk. Because Quora is so write-heavy, with millions of upvotes, comments, and new answers constantly streaming in, this sequential writing process drastically reduces the disk I/O bottleneck.
That makes total sense. They changed the fundamental physics of how the data hits the hard drive.
And there's a bonus. RocksDB has significantly less space amplification, meaning it compresses the data much more efficiently on the disk than HBase did.
Oh, so it saves them massive amounts of storage hardware, too.
Exactly.
Okay, upgrade number 4. They completely replaced those manual in-memory manager and worker queues we talked about in the initial design. Because obviously, if a server loses power, an in-memory queue just vanishes, taking all the pending tasks with it.
It's a huge liability.
So they replaced it with Kafka.
Yeah, Kafka is non-negotiable at this tier of system design. It is a highly durable, distributed event streaming platform.
So it doesn't forget tasks.
Never. Instead of a volatile memory queue, which is, it's like handing a sticky note to a coworker who might suddenly quit. Kafka acts as an indestructible, decentralized ledger. When a user uploads a heavy video, the service host doesn't process it. It just writes a task to Kafka.
And Kafka bolts that task to the floor.
It writes it to disk and replicates it across multiple nodes instantly. Then background worker servers just pull tasks off that Kafka stream at their own pace.
That's super clean.
It completely decouples the heavy asynchronous jobs from the live user experience. That ensures the front end never freezes while a background video is rendering.
The technology stack tying this all together is a really fascinating mix of tools. The sources note they use Python for the core business logic, which allows their engineering teams to develop and iterate features incredibly fast.
Python is great for developer speed.
But Python has limitations with concurrent processing due to its global interpreter lock. So, for the heavy lifting of routing millions of requests, they rely on C++A, because C++ operates much closer to the metal and provides that raw execution speed.
It's the muscle of the operation.
And they also implement long polling for the client connections. Instead of your phone constantly pinging the server asking, are there new comments? Are there new comments? The server just holds the connection open in a suspended state.
Like an open radio channel.
Right. In the millisecond someone comments on your answer, the server pushes the data down that open pipe instantly.
It's a beautifully pragmatic architecture. I mean, they aren't dogmatic about using one language. They use Python for developer velocity, C++ for raw network throughput, and Kafka for indestructible state management.
Okay, so we've overhauled the engine. We've got service hosts eliminating network hops, vertically sharded databases protected by memcached, Myrox writing data sequentially, and Kafka handling the asynchronous heavy lifting.
The whole package.
Now it's time for the final report card. We need to evaluate if this architecture actually meets the core non-functional requirements.
Because if we connect this to the bigger picture, evaluating an architecture isn't just about clocking its speed. The sources run through a strict compliance checklist.
Okay, let's hear it.
Is it scalable? Yes, the homogeneous service host can be horizontally scaled infinitely behind the load balancers. Just add more machines. Is the performance there? Yes, boosted massively by Myrox, the C++ routing layer, and that aggressive caching strategy.
Okay, but what about availability? How do they ensure the system stays online when individual servers inevitably catch on fire or just suffer hardware failures?
They maintain availability through configuration management services like Zookeeper.
Zookeeper, how does that work?
Zookeeper basically acts as the air traffic controller for the entire distributed system. It constantly maintains a heartbeat with every single server.
Just checking in, are you alive, are you alive?
Exactly. If a database node suddenly drops offline, Zookeeper instantly detects the missing heartbeat. It then triggers an automated leader election to promote a backup node and routes all new traffic away from the dead server before the user even notices a glitch.
That is slick. Which brings us to the most terrifying engineering scenario of all. Disaster recovery. What is wild to me is that in the blueprints for the initial design, disaster recovery wasn't even mentioned.
I know, it's pretty shocking.
It's like building a state-of-the-art skyscraper and just forgetting to install fire escapes.
It's a very common oversight in early-stage engineering, honestly. A system can be perfectly scalable and lightning-fast locally, but if a hurricane or a massive power grid failure takes out your single primary data center, the entire business ceases to exist.
So how did they solve this in the final design?
They implemented daily snapshots and backups of the databases, sending them to Amazon S3, which is a highly durable object storage service, in one specific geographic zone.
But backing up to one zone isn't enough, because natural disasters can wipe out entire regions.
Precisely. So they utilize cross-region replication. The backup data in that first S3 zone is continuously replicated to a secondary S3 storage facility in a completely different geographic region.
So there's a backup of the backup.
Exactly. If the U.S. East data center goes completely dark, the engineering team can spin up new application and database servers and restore the platform's state from the S3 storage in U.S. West.
Okay, but let's talk about the physical reality of this. Let's go back to our meteor. If the snapshots are done daily and they rely on cross-region replication, what happens to that brilliant, highly upvoted answer I posted just 10 minutes before the meteor hits the primary data center?
This raises an important question about the fundamental, inescapable trade-offs in distributed system design. You've hit on the crucial difference between synchronous and asynchronous replication, and it all comes down to the speed of light.
Because data has to physically travel through fiber optic cables.
Yes. With synchronous replication, the system would prioritize absolute data safety. So your new answer wouldn't be considered posted, and you wouldn't get a success message on your screen until that data was saved in the primary data center, sent across the country to the backup data center, saved there, and a confirmation signal was sent all the way back.
Which would guarantee my data survives the meteor.
It would. But the round trip for light through fiber optics from Virginia to Oregon takes about 70 milliseconds.
That doesn't sound that bad.
In compute time, that is an absolute eternity. If you force the user to wait for cross-country round trips for every single upvote, comment, and text edit, the application will feel incredibly sluggish and unresponsive.
Nobody would use it.
So they don't do that.
They don't. To keep the platform feeling lightning fast, they utilize asynchronous replication. When you post your answer, it is saved locally in the primary data center, and the system instantly tells your phone, success.
Done deal.
Then, in the background, it eventually replicates that data to the secondary region.
Which means
Any data written in that tiny, vulnerable window between the last successful background replication and the meteor strike is lost forever.
wow.
The engineers are making a deliberate, calculated trade-off. They are willing to sacrifice perfect data durability in a disaster scenario just to ensure the UI feels snappy and frictionless for the user every other day of the year. So what does this all mean? We started today by looking at a simple blank text box on a screen. And beneath it, we've uncovered this sprawling, hypersynchronized ballet of service hosts, Kafka event streams, LSM trees sequentially writing to myRocks, and 42 petabytes of data being slung asynchronously across the globe.
It's a testament to the fact that modern convenience is powered by staggering, almost incomprehensible complexity. I mean, the seamlessness of the user interface, the fact that it all just works when you hit enter, is a carefully orchestrated illusion maintained by thousands of servers and meticulous architectural trade-offs.
The next time you get an instant answer or scroll through a feed that feels like it's reading your mind, remember the invisible engineering marvel working overtime to defeat network latency just for you. But I want to leave you with a final thought to mull over today. Everything we explored today, the massive distributed caches, the 4,700 servers, the vertical sharding, all of this infrastructure was built primarily to handle text, some images, and a little bit of pre-recorded video.
That's right.
I mean, think about it. As platforms inevitably transition to generating high-definition AI video answers in real time for hundreds of millions of users simultaneously, what kind of completely unimaginable alien architecture is going to be required to keep that system from collapsing?